Welcome to The Explainer. Today, we're diving into the fundamental force that, honestly, underpins just about all of our modern tech. We're talking about electric charge.
So, what is this invisible force that runs everything from your phone to a bolt of lightning? The answer isn't magic, even though it can definitely feel that way. It's actually one of the most basic fundamental properties of matter itself.
Okay, so to really get a handle on this, we've got to zoom way, way in. I'm talking down to the smallest possible scale, to the absolute basic building block of every electrical thing you could imagine, the electric charge. And here's the key thing to wrap your head around. Charge isn't something that matter has, like an accessory. It's part of what matter is. It's woven right into the fabric of reality. And it comes in two, let's call them flavors. So, deep inside every single atom, you've got these two main characters. In the center, you've got the proton, holding on to its positive charge. And zipping around the outside is the electron, with its negative charge. These two are the essential positive and negative forces, kind of like the yin and yang of the entire electrical world. All right, so these properties are basically the rulebook for how charge behaves. The first two, they're pretty straightforward. You can add charges together and you can't just create or destroy them out of thin air. But that third one, quantization, now that's where things get really interesting. It's a seriously mind-bending concept that points to a deep secret about how our universe is built.
What does that even mean, quantization? Well, it means that nature doesn't do fractions when it comes to charge. It only deals in whole packets. Think of it like this. You can have 1 electron's worth of charge, or 2, or 1,000, but you can never have half an electron's worth. It's just not possible. And this is actually a huge clue that the universe, at its most fundamental level, is kind of digital. It's a cornerstone of quantum mechanics. Okay, so we've established we have these little packets of positive and negative charge floating around. But how do they talk to each other? How does one charge over here even know that another charge exists way over there? The answer lies in a really elegant bit of physics called Coulomb's law. It's built in a couple of steps. First, the bigger the charges, the stronger the force between them. Makes sense, right? But second, and this is key, the farther apart they are, the weaker the force gets, and it drops off super fast. You put those two ideas together, and boom, you get the complete formula that perfectly describes how they interact. This really just boils it all down, doesn't it? More charge, more force. More distance, less force. And this simple, powerful relationship is behind, well, everything. From static clay making a balloon stick to your wall, all the way to how atoms themselves bond together to create the molecules that make up you and me. But hold on a second. There's still something a little weird here, isn't there? This whole idea of a force at a distance, it feels a bit like spooky action. How does that charge actually reach across empty space to push or pull on another one? So is it magic? Nope. But the answer is almost as cool. It's an invisible field of influence that fills the space all around a charge. And physicists have a name for it, the electric field. The best way to think about it is like an aura, or a sphere of influence, that a charge creates in the space around it. It literally changes the fabric of space. So if another charge wanders into this influenced region, it feels that disturbance as a force. The electric field is like the messenger, carrying the news of the force from one charge to the other. And this idea gives us a really powerful shortcut. I mean, if we can figure out the strength of the electric field at any point in space, we can instantly know the exact force it would put on any charge we decide to drop there. Super useful. And check this out. This is what so elegantly explains why opposites attract. A positive charge, it gets pushed in the same direction as the field lines, but a negative charge, it gets pushed in the complete opposite direction. It's like they're programmed to react in fundamentally different ways to the very same influence. Okay, so we know how individual positive and negative charges behave, but what happens if we take one of each and stick them together, separated by just a tiny distance? Well, then we get something called an electric dipole, and these things are everywhere in chemistry and physics. It might sound simple, just a pair of charges, but it's a huge deal. A perfect example is the water molecule, H2O. It's a classic dipole. This setup makes it a tiny, electrically lopsided molecule. And that lopsidedness is the secret behind why water is so good at, well, being water. So now imagine you place this dipole into a nice, uniform electric field. Think of the field like a steady river current. The positive end of our dipole gets pushed downstream by the current, while the negative end gets pushed upstream.
What happens? The whole thing starts to twist.
This twisting force has a name. It's called torque. And notice, the dipole isn't moving from its spot. It's just spinning in place. It's exactly like how a compass needle twists to line up with the Earth's magnetic field. The dipole will rotate until it's perfectly aligned with the electric field. And get this is literally how your microwave works. It creates an electric field that flips back and forth billions of times a second, forcing the little water dipoles in your food to twist and turn like crazy, which generates the heat that cooks your dinner.
And, of course, there's a formula for that. This tells us exactly how much twisting force that dipole feels. So P is the dipole moment. That's basically a measure of the dipole's strength. E is just how strong the electric field is. And that sine theta part, that's all about the angle. When the dipole is sideways to the field, it feels the maximum possible twist. But as it rotates and lines up with the field, that angle goes to zero, and the twisting force, the torque, completely disappears. It's found its happy place, its most stable position.
Which brings us to a really fascinating question. We've seen how charges create forces and fields out in the open. But what if you were to completely surround a charge? Say, put it inside a box. How could you measure its total influence on everything outside that box? Answering that question leads to one of the most beautiful and powerful concepts in all of physics. But that is a story for our next explainer.